Okay, thank you very much. This class is on equilibrium constant. Equilibrium constant is a ratio of products to the reactants. Okay, I give you an example. Here, nitrogen, this is gaseous, reacts with hydrogen, it's also gaseous. These two reacts to form ammonia gas. This is a gas, and for balancing, here is 2, here is 3. Okay, so we start with the reactants. When the reaction starts in industry, that's with the reactants only. Reaction proceeds, gradually the products, ammonia increases. And when the reaction stops, I mean reaches dynamic equilibrium, we say the reaction is stopped. Basically, the reaction is still on because this is dynamic equilibrium. Here are two reactions still on: forward reaction, backward reaction. Both are producing the substances, but amount of the substances, products or reactants remain constant. So their concentrations do not change. But before reaching the dynamic equilibrium, this concentration will be changing. Okay, so you got reactants with high concentration of reactants that will decrease gradually, and concentration of products will increase gradually as the reaction proceeds. But after a certain time, they will be stable. When they are stable, there is no more change. Only we measure or we estimate Kc. The Kc is the equilibrium constant, and the equilibrium constant, the term is only when the reaction reaches dynamic equilibrium. This cannot be beforehand. Understand? This cannot be beforehand. When reaction is on, reaction going on, you cannot estimate or talk about any Kc. The reaction has set equilibrium, then we say this is Kc. Kc means concentration of products. Here products, only one products here, and with third bracket we mean that this is concentration. So here is concentration of the product, only one product here, ammonia, and two reactants. These are nitrogen gas. I'm not giving here the state symbols. Basically state symbol is very important, but for quick writing, this is there. Concentration of products divide concentration of reactants. The stoichiometry there is to be here as power to the concentration. And here is nitrogen, no number before this, but before hydrogen you get 3, so 3 will be here. So this is equilibrium constant. Equilibrium constant equals this, and this equilibrium constant is in terms of concentration. The concentration is C here, C is CT in terms of concentration, right? This can also be in other way. Then we write Kp. Okay, this is the Kc. Now our main job is calculating the Kc. What's the value of Kc? Kc is very important. In the industry, when we carry out the reaction, we expect high Kc. Kc is high because when you get Kc high, which means you have large amount of product compared to the amount of reactants. Okay, because here products divide reactants. Products divide reactants with the Kc. So big value of Kc is expected. We expect that. So now how to get this? How to calculate this? We are starting with a typical question, with a very typical question, which may be here certain amount of, for the reaction in the industry, will start certain amount of nitrogen and hydrogen. Okay, certain amount of nitrogen and hydrogen, and when the reaction reaches dynamic equilibrium, we will calculate the Kc for the reaction. Okay, clear? And suppose our reaction in a reactor, certain mole, I say mole, certain mole or mass or volume, any amount given there. Understand? We start with first mole. Better we say mole. Certain mole. Maybe here I write where is that? 0.7 mole. Okay, think that 0.7 mole. Suppose there 0.7 mole of nitrogen, and here maybe 2 mole. Here this is also mole. I write 0.7 mole of nitrogen and 2 mole of hydrogen. these two gases are mixed together for the reaction and set the condition required for the reaction. The 450 degree centigrade temperature and catalyst and pressure 200, around 200 pressure requires for the reactions. So these conditions are set there in a reactor. I say in a reactor, and these two gases are mixed there at this ratio, in this amount. And when the reaction reaches dynamic equilibrium, certainly this amount will decrease, right? This two amount will decrease when the reaction reaches dynamic equilibrium. And you don't have this at the beginning, but the reaction will produce this. Reaction will produce this. Okay? So when reaction reaches dynamic equilibrium, what's the value of Kc? That's our topic. So look at the expression of Kc. To calculate Kc, you need to know the concentration of the products and the reactants. And certainly you understand, you know that there's values given here. Here's no value given. This is 0 mole. At the beginning, you have this 0 mole, right? You don't have the reaction started at the beginning. You just have this mole of nitrogen or this mole of hydrogen or any other amount so you start with. But product will be 0. Okay, everybody understand? And you need the concentration. You need their concentrations. And the challenge is this concentration, this 2 mole will decrease. And this mole 0 here at the beginning will increase. Okay, so you need to know their moles first. Remaining mole of the reactants and the mole of ammonia produced in the reaction. Understand? Remaining mole of the reactants and mole of products produced there, you need to know. If you can estimate or calculate after the reaction takes place, you can estimate their mole and then to calculate their concentration or convert into their concentration, you will have to divide with their volume, right? Volume. So another information you need to know, another 2 pieces of information you need to know for the calculation. This is one. This information is you need volume. Okay? Without volume, you cannot calculate concentration. Understand everybody? The volume maybe I just give here 2 dm cube. Take that this is 2 in a container which has volume 2 dm cube. And another thing you need what percentage of reactants will convert into products. Okay? This to be there. This to be given there, because without this information you cannot estimate the remaining amount or the amount of products produced there. And suppose here we give this information that 10%, I write here 10% nitrogen reacts. If you get this, 10% nitrogen reacts. Okay? So when you have this 2, you can estimate their moles and you can estimate their concentration. Okay, understand everybody? So how is that? You need to draw a table. You may draw a table for this calculation, simple table. And look at the table I draw. Firstly, you have nitrogen and then hydrogen, and then the other thing will produce the ammonia. Everybody clear? These 2 are reactants and this is the products. At the beginning, before the starts reaction, you have what you have. I write here mole. This is the units. This is for units. The first one is mole. What the mole given? Nitrogen 0.7, and this is given here 2 mole. And what's the mole of ammonia at the beginning? 0. Very good, 0. And from this changes by 10%. 10% nitrogen reacts. This is the change of nitrogen. So if change is there 10%, I can write its initial amount. Okay, this initial amount. Then here is another, this for change. I write here change. Okay, get the change. If 10% of 7, so what is that? What is the amount? 10% of 7? 0.07. 0.07. So look at this here. I put a minus sign. The minus sign means this is negatively changed, will decrease. Are you clear? If this is for reactant, there should be minus. Everybody clear? This was the initial mole, and it says the change 10% nitrogen reacts. So what is the 10% of 0.7? Very simple. This is there. So 10% estimation kore ekhane likhte hobe. This 10% there. Okay, everybody clear? And now What about these two other substances? Okay, these two other substances we can get from the stoichiometry. What is that? Understand? Stoichiometry means the ratio, mole ratio. Mole ratio. You already know. The ratio is given here. 1:3:2. Okay? This is how they react. 1:3:2. If this reacts 1 mole, this will be 3 mole. This will be 2 mole. If this reacts by 0.1 mole, if this reacts by 0.1 mole, 0.1 mole, this will be here 0.3 mole, and this will be here 0.2 mole. If this reacts 0.2 mole, 0.2 mole nitrogen reacts, what would be the mole of this reacts? 0.6 mole, and the ammonia will produce 0.4 mole. So this is how they work, right? So here the amount is given, change, that is the actual amount that reacts. So this amount of nitrogen reacts, this mole of nitrogen reacts. Okay, so use the ratio. When this mole of nitrogen reacts, so what mole of hydrogen will react? So isn't 3 times than this? Remember, the change we can estimate by comparing in the equation. As per the equation, 3 times the nitrogen. Okay, this 3 times the nitrogen. So what's the 3 times of this? This is a 0.21, right? This is the mole of hydrogen will react. You got 2 mole, but this mole reacts only. And now what about this? Ammonia. From the ratio
0.14.
This is double of the first one. Understand? This is double of the first one. The first one is given here nitrogen. And what's the double of this? 0.14. This time, this is not negative. Okay, this is not negative because this is the product forms in the reaction. These two are reactants, so they're minus because the amount decrease, and this is form. So you may write here positive. Okay, positive forms. So this is how we can estimate the other amounts from any change. Is this clear to you? তোমরা সবাই পারবে একটা amount change from one change you need to estimate the other changes. পারা যাবে? Clear? This is very simple as you get in the ratio. Now we just balance the amount. So final amount, which is the equilibrium amount. The reaction reaches equilibrium. So I write here equilibrium. This is equilibrium amount. So you got here 0.7 at the beginning. This is gone. So what mole remains there? 6.03, right? Or 0.6. 0.63, right? 0.63. So this amount remains there. You started with this mole and this mole gone. So remaining mole is this. When reaction reaches dynamic equilibrium after the change, after the reaction takes place, after this decreases, the remaining amount will be this. Reaction is at equilibrium with this mole of nitrogen still there. And now about hydrogen. Look, for hydrogen here will be already set. This is already set. This was 3 times of the first one. Remember, this was 3 times of the first one. And you had this at the beginning. So what mole remains there? 1.79 mole. So this mole remains there. This mole of hydrogen will remain there. And what about the ammonia? Ammonia is produced. This was 0 at the beginning. Now get 0.14 mole. Understand? Everybody understand? This is also mole. Change is also mole. The remaining mole is also mole. So is this clear to all of you? Very simple. Now we got the volume. What's the volume given here? 2 dm cube. And you already have the moles, remaining moles. When reaction is no more producing reactants and products, there is no more change. At this time, you got these 3 moles, and you have the volume, which is 2 dm cube. Now, if you divide all of them with 2, you're getting the concentration, right? You're getting the concentration. So I write here concentration. How is that? 0.63 divide 2. I get here 179 divide 2. 0.14 divide 2. So I'm dividing all of them with 2. 2 is the volume. So what do you get? This unit is mole per dm cube, because we are converting into concentration. So what do you get here? 0.315. Good. 0.315. This is mole per dm cube. The concentration of nitrogen, remaining concentration of nitrogen is this. And what is here? Hydrogen, for hydrogen 0.895. Okay, then this is 0.7, right? 0.07 mole per dm cube. So these are concentration. Now look at the expression. Look at the expression. You already have calculated concentration. If you just put the values here, you will easily calculate the concentration of Kc. That is show here. I'm going to show this one of them here with units. The value here of ammonia, what is that value? 0.17, sorry, 0.07. I write the unit mole per dm cube square. Okay, this is a square here. And what's the mole of nitrogen, concentration of nitrogen given here? 0.31315. Okay, this is here again, mole per dm cube. No square here. This is, and another is 0.895. This is also mole per dm cube. And this is here with cube, right? Cube. So now you simplify to get the answer. Simply you need calculator. You'll get some values. Remember, here is a square and here is a cube on them. So you just estimate. Calculator say. And the units there. Here is mole per dm cube. Mole per dm cube square. And here you have mole per dm cube. Mole per dm cube. And another mole per dm cube. Cube. So on simplification, you get here mole per dm gone. So here will be 1 divide mole per dm cube 1 by mole per dm square. That gives you mole minus 2 dm 6. This will be remaining units. So what do you get here? 0.022. Okay, 0.0. So this is the value of Kc. Clear? Everybody clear? Online jara acho bolo.
Sir, clear.
So I hope you are clear with this calculation, and now we are going to have some practice. আমি এখন practice করতে যাব, but before that, if you have any problem with this calculation, how to estimate the concentration. First, main job is estimating the concentration. This is the main job, and putting the values there in the expression and calculation is very simple. Main job is what is the main job? Calculating concentration. Is this clear to you? So I open the note and start another practice for you. Just a minute. Start this. This is here chemical equilibrium. So you need to calculate. You should be prepared with copies and pens. Get here the calculation. I show you one again. You may see another. You may see here another again. Now look at the table. What does it say? How to draw the table? Dekho Kc. Calculation of Kc. Everybody here? Calculation of Kc. How to get it? Okay, this must be done using the equilibrium concentration values. Draw a table. Okay, draw a table with initial number of moles. Remember, you may not be given all the times moles. Okay, that may be given, there may be given mass or volume, etc. Then you will convert them into their moles. That is very simple. And then the change. The first row will be there for the moles, and second row will be for the change. Okay, any change from any change you can estimate other changes. The substances and equilibrium moles, adjusting the initial and change, you can estimate the equilibrium moles. Then you got to convert the equilibrium mole into concentration. This is by dividing the volume. Volume will be given. The expression of Kc, put the values there and calculate there. So I show you another. Just see this. That's not for your calculation. An important reaction here is question. An important reaction in blast furnace is the formation of carbon monoxide from carbon and carbon dioxide. The reaction is an example of heterogeneous equilibrium because it is solid and gas too. Remember, when 1 mole of carbon dioxide gas was heated with excess carbon means there's no shortage of carbon. Temperature is 700 degrees centigrade and the volume, total volume given 20 dm cube. It says 95% of carbon dioxide reacted. So look at the equation. In the equation you get here 3 substances, but in the table you just consider 2 substances because one of them is solid and solid doesn't appear in the equilibrium expression, right? Solid is not there. So initial amount, what is given in the course and the statement, given that mole of carbon dioxide is 1 and that of carbon monoxide is 0. So no carbon monoxide there. So mole is here, right? Look at the change. Change given 90. It says 95%. 95% of 1 is 0.95. Okay. Then you get this is double. So you may have problem with this. Remember, here may have problem. This is here 1 and this is here 2. So the ratio matters here for the change. This will be double change. Okay, then the first one. This is still mole. Equilibrium amount, adjust this 2, subtract this 2. 0.95 from 1 and this is here product added together you get the equilibrium mole. Now you are dividing all of them with 20. 20 is the same volume for all the substances together. Okay, reaction mixer are in the same volume. So now expression, look at the expression. You shouldn't add there C carbon. Carbon cannot be there because carbon is solid. So now put the values. After you put the values, simplify along with the units. So you get here 3.61. Clear? Are you clear? I hope you are clear. Now you do another calculation. Okay. And this is little different, very little different. It doesn't say this. The next question doesn't talk about the chains. Instead of chains, here is given the remaining mole, equilibrium mole. Understand? Equilibrium mole of one of the substance given there. And excuse me, listen carefully. From this remaining mole, you will have to estimate the change. What is that? Which substance is there? Iodine, right? And initially you certainly have some iodine, right? Initially you have, what's that? Where's the product? 0. Initially you have iodine 0, and when reaction is finished, you get this mole of iodine. So what's the change? What's the change of iodine? Yes, just this positive. Okay, this positive will be changed because initially there was 0 and ultimately you get this amount remains there. Certainly this was the change. So from the change of this, you can estimate the other changes. Understand? Other changes. So start solving this. Everybody start solving this. Come on.